Drop raw sodium into a beaker of water, and it immediately tears itself apart. The metal sparks, rapidly expands, triggering a violent explosion. But if everything in the universe is made of atoms, why do these specific elements rip each other to shreds instead of just floating peacefully side by side? It happens because the universe is inherently restless. All matter is constantly driven by a strict physical rule. It wants to reach a state of lowest possible potential energy while maximizing entropy, the total amount of disorder in the system. Think of a boulder perched on the edge of a cliff. It naturally wants to roll downhill to decrease its stored potential energy. That explosive chemical reaction is just the atomic equivalent. The elements are violently rolling downhill, dumping off their excess energy to reach a lazy, stable state. To understand exactly why atoms carry so much tension in the first place, we have to look all the way down to the subatomic scale. The positively charged nucleus and the negatively charged electrons surrounding it. These electrons do not orbit the core in neat, predictable circles like planets around a sun. Thanks to the equations of physicist Erwin Schrödinger, we know they actually exist in probabilistic wave functions. They are hazy clouds of chance. Electrons occupy highly specific three-dimensional regions in space around the nucleus, called orbitals. Some are spherical, some look like dumbbells, but they all represent the physical area where an electron is most likely to be found. To keep their potential energy as low as possible, electrons follow a strict mathematical sequence. They populate these subshells from the inside out, starting close to the nucleus and layering outward until each shell hits a precise maximum capacity. The problem is that most elements in the universe do not naturally possess the exact right amount of electrons to perfectly finish their outermost shell. They are left with gaps. Having an incomplete outer shell forces an atom into a state of high potential energy. That invisible subatomic tension, the desperate need to find a few more electrons to finally close out a shell, drives almost every chemical behavior. If you look at this historical Portuguese periodic table, the group numbers at the top of each column, Roman numerals 1 through 8, aren't just a filing system. They map out atomic desperation. Elements in the same column have the exact same number of outer electrons. Because different elements have different numbers of protons in their cores, they pull on incoming electrons with varying levels of strength. We measure this pulling power as an atom's electronegativity. When a very strong atom meets a weak one, it completely steals an electron, creating a rigid ionic bond. But if they pull with roughly the same strength, they form a covalent bond, mutually sharing outer electrons to complete their shells. Metals solve the problem entirely differently. In a metallic bond, the outer electrons abandon their loyalty to any single nucleus. They spread out and flow freely through a massive, delocalized grid, which is why pure metals bend easily and conduct electricity so well. None of these chemical bonds are physical tethers. They are simply energy compromises forged by unstable atoms cooperating to reach a full outer shell. Even when molecules share electrons, they rarely share them perfectly equally. When one atom pulls slightly harder, the shared electrons spend more time on that side of the molecule. This creates a permanent electrical dipole. One end carries a slight negative charge, while the other becomes slightly positive. Because opposite charges attract, these tiny poles constantly tug on entirely separate molecules floating nearby. These attractions are called intermolecular forces, and they cause trillions of distinct molecules to constantly arrange and rearrange themselves around each other. The strength of that tug of war directly dictates states of matter. At low temperatures, molecules lack kinetic energy, locking into rigid, solid structures. Warm up an ice cube, and the molecules vibrate fast enough to break that rigid grid, sliding past each other as a flowing liquid. Add enough heat, and they break away completely to expand as a chaotic gas. Push the energy high enough, and the physical atoms themselves get ripped apart. The electrons separate entirely, creating an ionized gas called a plasma. As loose electrons crash back into lower energy states, the sudden drop in energy releases visible light, exactly what illuminates these Las Vegas neon signs. Everything we touch and see, the rigidity of ice, the flow of a river, the colors of a glowing sign, is simply the macroscopic result of microscopic electrical charges fighting for balance. So what happens when two different, fully formed substances collide? For a reaction to occur, the molecules must break their current bonds and form brand new ones. But they will only do that if the final arrangement results in a lower combined energy state. We calculate this using a master mathematical equation known as Gibbs Free Energy. Delta G equals delta H minus T delta S. By weighing the internal heat of the system against its total amount of messy disorder at a given temperature, Gibbs Free Energy determines if a reaction will happen spontaneously or if it will require an outside push. This exact mathematical logic governs acid-base reactions. Acids are simply molecules primed to throw away a positively charged proton, specifically a hydrogen ion, while bases are molecules eager to catch them. As they trade protons back and forth, they hunt for a stable equilibrium, a balance we track using the pH scale. It also drives reduction-oxidation or redox reactions. Instead of tossing around protons, these atoms trade entire electrons to optimize their internal charges, continually adjusting their oxidation numbers until the energy math settles out. From a nail quietly rusting in the rain to the stomach acids breaking down your lunch, every chemical reaction on Earth is just matter obeying the strict arithmetic of Gibbs Free Energy. That violent sodium explosion is a precise, calculated transfer of atomic wealth. Because of the conservation of mass, we can use stoichiometry to track the exact ratios of the reaction. Between the starting metal and the resulting salt water, 0 atoms were destroyed and none were created out of thin air. They were entirely conserved and precisely rearranged. The massive burst of heat and gas was the physical expulsion of excess internal energy that the sodium and water had to throw overboard so their newly joined atoms could finally achieve full outer shells. Chemistry operates as a singular, elegant system governed by a few fundamental laws of energy that remain consistent across every formula and exception. From hazy quantum probability clouds mapping out subshells to the roaring combustion fires of a chemical explosion, all of it is simply the universe balancing its ledger, constantly trading pieces of itself to finally find a little peace and quiet.